Okay, so this is the final non-parametric test that we're going to look at in this series. This is the third test, or the fifth, depending on which way you look at it. It might be worth summarising the tests we've done. We've looked at the sign test for single sample. And we've also looked at the Wilcoxon signed rank test. Wilcoxon signed rank test for single sample also. But we've also looked at those so those are the two tests, but we've also looked at those for paired data, where you got data that automatically seems to go together, like we did an example with the scores, golf scores before input bad and for the same player in bad and good weather, and compared the two, so where they were paired. So those are kind of 2 or 4 tests that we've covered, but all non-parametric that we've covered so far. Now the Wilcoxon Rank Sum test, well, here we're basically comparing the medians, of 2 sets of data. But I suppose it's important to say that they are unpaired. So it's not like our golf example, we've got 2 sets of data, but they don't automatically match up. It should become apparent in the example we're going to do. So it's always for unpaired data is this one. The data size doesn't, the sample doesn't need to be the same size. So the example we're going to see, for example, here, they're not the same size, and typically they won't be in the examples that we do. So yeah, that's it. So they may well be of different size, but notice this example here. We're looking at the number of students from a university geography course, and test whether there's a difference in the performance of the 2 groups and select some marks. So these aren't necessarily of students. These aren't the same students in any way. They're different students, so they're unmatched. So therefore, we're looking at the rank sum test to compare the medians of the 2. The assumption, and we've seen this kind of assumption before with some of the tests that we've seen, is that the shape of the distribution is the same. So we can have this, but it has to be, and they could, obviously the position might be different. They differ in the median, so they differ in position, possibly, which is what you're trying to test. What we are conducting hypothesis tests for. Okay, now thankfully the process is explained. This is for further maths again. If you're doing further maths OCR, the process is explained in the formula book with the tables. I've just so it's a little bit to remember, but not really too bad, because we are given a kind of crib sheet to work from, so it shouldn't be too bad. Okay. Incidentally, I think I've mentioned this before. This is directly equivalent, or basically the same as the Mann-Whitney U test, but it's slightly different process, I believe, but it does the same thing. So you'll get the same outcomes on this than you would do with a Mann-Whitney U test. So they're the same. Okay, so the conditions are the same or whatever. Right, so let's do this example. Okay, and let's look, we've got the crib sheet above. So let's write out our null hypothesis, that they're basically the same. Median of both sets of students the same. So H1 is the median are not the same. I don't think, looking at the question, we're given any hint of direction. It says stating any necessary assumptions. So same shape is the assumption, assuming shape of distribution for both sets is the same. Okay. Right, so assuming the shape of distribution for both sets is the same, and we're testing on the median. And what we do, we write out the data, and we basically put in the ranks of the data from smallest to largest. I think I might just copy it down here. I've just rejigged the layout here, and remembering that the crib sheet that we have is here. That's in the formula book that you're given. So the first thing is the two sample sizes of m and n, where m is less than n. So we can say that m is equal to 1, 2, 3, 4, 5, 6, and n is equal to 1 more, so n is 7. So n is the larger of the two. So just going back to the point that we said earlier, this is not paired data, and the fact that we don't have the same data, we don't have the same amount of numbers is a giveaway. But of course, it could still be the same. They could still be the same. Like I could have another one there, and still not paired, because they don't fall into. We're not talking about the same students. It's not naturally. These two don't naturally go together. It's just happened to be lined up, but they're not lined up in any. It's arbitrary. So it's not paired data. Okay, so let's get on with this. So first thing we have to do, it says Rm is the sum of the ranks of the items in the sample size m. Right, so the way we do this, basically just rank, regardless of which set they're in, these in order from the smallest first. So this one is the smallest, 30. Okay, 36 is the next smallest, and then 40 is the next smallest, and then 48, and then 49, and then 51, then 52, then 56, then 59 is the 9th, then 62 is the 10th, then 11, 12, 13. Rank them like that in order, but taking care. It's easy to mess up, really. So taking care that you actually have ranked them in order and haven't, got them somehow mixed up. So then it says Rm is the sum of the ranks of the items of size m. So it's the sum of these. So Rm equals to all of these added together, 1 plus 2 plus 4 plus 6 plus 9 plus 10. And that equals to 32. Then you work out this quantity here. It seems a bit strange, but I'll talk a bit about that in a moment. Minus Rm. So that's equal to, m is equal to 6 times 6 plus 7 plus 1. Take away the Rm, which is 32, which is 52. And our test statistic W is the smallest. of these two values, the smallest of 32 or 52, which is 32. Now, yeah, it seems a bit strange, this. It just actually helps us. It can be proved, but basically if we were to rank them in the opposite order, so in other words, this one was 1 and so on, then this number here would be what our RM would be if we went the other way. It's just quicker to do it this way. Okay, it's just a little bit of pure maths there to prove that. So then, yeah, so we want the smallest one. So our W value, our test statistic, is 32. Right, so now it's a case of looking in the tables for the appropriate critical value. Right, so here's the tables that were given, and we look for, we've got M as being equal to, M was equal to 6 and N was 7. So we've got 7 by 6, we're looking at that row, and it's two-tailed, and it was 10%, I believe, going all the way back, 10%. So it's 10%, and so we're looking for 10% two-tailed, 10%, so the critical value is 29. So that's our critical value, 29. So let's make some space here. So the critical value with M equals to 6, N equals to 7 at 10% two-tailed equals to 29, which is less than, let's write it over here, is less than 32. So because of the nature of this, and sometimes you can forget the process, I find this so unintuitive at times, but thankfully in the formula it does say for each pair of values of M, the table gives the largest value of W, which will lead to rejection of the null hypothesis. Okay, it's the largest value of W which will lead to rejection of the null hypothesis. Our test statistic is above that, so the largest it could be is 29 for us to reject the null hypothesis. 28 would reject it, but we've got 32, so we're the wrong side of the critical value for us to reject H0. So we do not reject H0. There is insufficient evidence to suggest that the median score of the students who were provided the filmed lecture is different to those that attended the theatre. I've probably written more than I need, but you do need to give a contextual statement at the end. So that's certainly going to be there. There are some key things. We've got to use the fact that have a nod to the fact that it's two-tailed, they're different, and we've got to actually talk about what the actual test was about in context. Okay, so that's an example of the Wilcoxon Rank Sum test, which concludes all the tests that we need to look at, except we've only looked at the Wilcoxon versions of the test, both the rank sum test and the assigned rank test, using these tables. for smaller samples. If the samples are larger in both cases, we have to use something called we have to use a normal distribution, because it can be shown that these can be approximated to the normal distribution. So the final lecture in this series will be on how to use a normal distribution for the Wilcoxon tests. Okay, that's it for now. Bye.